box on this thing. Let's go up. Let's just see the whole thing right there. Let's go over to here. Let's go up. Let's go over. Looks like a good place to start. It's doing something. Looks like we've gotten it where it crosses. Aw, man. We missed it, right? So we need to go down even further? Correct? So let's go down even further. So let's check the window here. What do you want? We need to change which value? Y min? So let's go to negative 20. I don't know, negative 50. The problem with this is it's going to look all squinched, right? Let's see. Does it actually get down there? Let's see. Whoa. Okay. Did we go down far enough? Doesn't look like it, right? It really doesn't look like it. So what do you want to go and graph this thing? Maybe this will help. Maybe we'll see something. Are we seeing anything? So let's widen it out a little bit and see if we can see something. So let's make it, how about negative 0.5 to 0.5? Let's just see if we see anything. Oh, there seems to be... Should we see it on the other side too? Ah, yeah. So what does this mean we need to do to our window? Nope, not widen it. The Y min has to be much far down, right? So how about negative, let's do 10,000.
If you put Y max at 5, it's going to get a lot easier for you.
Y max at what?
5.
5, like this?
Yeah.
So if we graph this thing,
It crosses it at 4.
what's the problem?
Hi.
Okay, it's spiking. Let's take a look at our window again. What's our window? We're going from negative 0.5 to 0.5, right? And we're going all the way down to negative 10,000. It looks like the graph is what? It looks like the graph is stopping. Is it actually stopping? No. Why does it look like it's stopping, though?
Because our Y values are small.
Why?
Because the graph or the
Yes, the Y values being huge makes it do something, but that's not why it looks like that. Yes.
calculator just determines a 0, or determines it's closest to the limit. So, or as you say, like arbitrarily close to as we get there. The calculator decides that you can't get there any closer and stops.
Kind of. That's not actually the problem. Does this graph actually keep on going down? Do those spikes actually keep on going down? Yes. Why isn't the calculator showing it to us? What's the problem? Why is it? It's not actually deciding to stop. It would love to. What?
The lines are so
It's too steep. It can't. It freaks out. It can't go any further in the steepness, so it just freaks out. I don't know at the coding level why. The point is, if we zoomed in right here, would we see something that looks like this? Would it just stop like halfway down? No, it would keep on going down, right? Let's just test that. If we zoom box, and you actually need to see what I'm doing. If I zoom box, right, let's go all the way over. So if I zoom box like right here, let's do that. All the way up to and then over like this. It only goes halfway down that box, right? But if we graph this thing, it's going to take a little while because it went all the way through, right? So does that thing keep on going down? It keeps on going down. It does keep on going down. So just to say that one more time. Resolution, bad. Calculator, dumb. Rounding hurts you. If things get too steep, what does the calculator do with the line? It just stops drawing it. That's why, like, on asymptotes, you see it all the time. You'll see things go like this and just stop.
It's like an intermediate skier.
It won't. It's like, I'm done. I'm done. I'm fleeting. I'm done. I'm done. What's one way we could do that? What's one way we can make that estimate? Yes.
If you put in 0.001 for x.
Yes, but remember I said you can't just do value. Doing one value is not enough because it could go berserk before it. So what do you need to do?
So you like 1 and then like 0.5.
Yeah. So what are we going to make with our calculator? What are we going to make?
Put
The function as. Okay. So first make the function. So what is it? It's 2 to the x minus 1 divided by x. And now what am I going to make?
Now look at the table.
Make a table. Exactly. That's what I meant. I wanted to say make a table. So table set. We're looking at it around 0, right? So let's go from negative, I don't know, 0.01. And let's go, I don't know, the step is 0.0001, like this.
Yeah.
And now we do the table for this thing. And what do we end up with? Looks like it's getting really close to... The reason we don't just do one value is we need to see a path of some kind. We need to see a path. It's kind of a hand-waving methodology because it's not exact, but we're not in the exact world yet for limits. You don't have many ways of finding exact limits except for simplifying and canceling things out. So right here we have this. So there is an error. Again, why is there that error?
It's 0.
You can't divide by 0. You can't divide. So we made a table of values for this function around 0, and we end up looking at to the left and to the right. The other thing is, if it's different on both sides, the limit doesn't exist. But on this side, does it look like the limit is the same on both sides? It really does. I mean, it kind of doesn't, but could we zoom in even further if we wanted to?
Yeah.
The problem with table value is that we're kind of limited because if you zoom in too far, do you remember what happens?
Goes to like,
It just starts rounding immediately. It cuts off really quickly in the table view. But if we use this, can we make a pretty good estimate? Yeah. Take those two values and do what with them?
average.
Just average them, right? Exactly. So you do them out. So it looks like it's, if we did 2 decimal places, 0.6969. It wants 3 decimal places,
Yeah.
so maybe 693. Does that seem pretty good?
Yep.
That's pretty good. Does that make sense? Yeah. Now, later in this class where you learn how to find that exact value, like what is that value? Absolutely, yes. And if you want to see it on your calculator, where's the button? There it is. Just as a preview of what's to come. Does that make you feel better or worse?
Worse.
You feel worse?
A little scared.
A little scared? What doesn't it doesn't make you feel?
Easier.
Isn't that so much easier just knowing that? But the question is, do you know where that comes from?
No.
No. But I'm just saying, is there a way to easily find that answer? Yeah. Then how long did it take us to make this table? Not very long. But it's important that you make that table. And then we have f of 1 is what? 1. I'm using different scales, that's right. And f of 4 is -1. Do we have any idea what it does in between? No, but if we wanted to make it easy, how about this? We just connect it. Done. Could it go berserk in between those two things? Yes. Yeah.
So how do we know how the graph comes into that one point? Does it matter for
As long as it comes into the point, it doesn't matter how it does. As long as that there's a path that's continuous that comes into it. Correct. Correct. But are there many different ways to do this? Sure. When I ask these questions, do I get many different types? Yeah. I mean, basically, to minimize this, like I say, using only horizontal lines or using only lines, what would you do? You would just turn all of these into, you would say, okay, it's going to go like that. And no bendiness. I would just go, yay, there it is. Stop. You're all done. What are we going to change it to? How about table start at what? How about -0.5 and go up by 0.1 just to make the step even more granular? So does it look like it goes to 1?
Yes.
Yes, it does look like it goes to 1. That's all it's asking you to do.
That's the
Okay.
answer for 21.
21 is asking, use a table of values to estimate the limit. If you have a graphing device, use it to confirm your result graphically. So you created a table, and what does the table tell you? As you get closer and closer to 0, what does the function go to? Oh, but it's not actually going to 0. What's it supposed to go to? I'm sorry.
One, okay.
You're right. It's supposed to go to 1. I'm sorry. That's to 0. So if we change this, I'm sorry. So we just change this table start. Let's change it to what? 0.5. Sorry. To 0.5. We go to 0.1 here. So now let's do the table. Sorry about that. Yeah.
Okay.
So what does it look like? It's an error, but are those decimals, are those decimals close enough together for us? I think they should be a little closer. So what do we change about our table? Let's start closer and make that 0.01. We do this now. And what do we end up with? Is it a little bit more, is it a little better?
Yeah.
It seems like it's a little better. Okay, yeah, it jumps. Should we go even closer?
Sure.
Yeah, I mean, it's not, those decimals are different enough that it doesn't seem like you'll get a rounding error if you go any closer. So we do second table set. Let's go to what? 0.99, 0.001. Second table. How's that path look? Looks pretty good. We want to get it around 1 though, right? So let's go down all the way to, is it even better? Yeah. So if we did this, how would you use these numbers right here to make your estimate for the limit? You could average them, yeah. You could average them right here, and they're actually not that bad. What does it look like that the limit actually is? Looks like it's actually exactly 0.6. It really looks like it's exactly 0.6. Yeah, it's cool. Right here, it says the limit of f of x as x goes to a is infinity. Now, can you ever equal infinity? It's an idea. It's a concept. So sometimes you see books, instead of using equal signs, they sometimes use like an arrow instead, because it's not actually equaling infinity. It's approaching. It's going to or approaching it, because if it doesn't exist, can you approach it? I don't know. So what that means is you can't have situations like this. The limit as x goes to 0 of 1 over x. For example, let's say 0 from the right. There's nothing to do with simplification. You can't really do anything super clever. So what should you look at? A graph, exactly. So you should know what this graph looks like. There it is. And what happens? It goes like this. Oh, doesn't cross. I slipped a little bit there. It's an asymptotic function. That's correct. So if you approach 0 from the right, what is this limit going to? It's going to infinity, right. What's the limit of this thing as x goes to 0 from the left? Negative infinity. It's going down, right? The point is you can have that. That can be the case. The limit of two things added together, you do.
The limit of the two functions.
And then add them together, yeah. So if you have like the limit of something, something, something plus something, something else, you can break it apart into two limits. What about minus signs? Oh, it's the same thing. C is a constant. So if you have the limit of c times something, what can you do? Take the c and essentially factor it out, exactly. You can do that last. That can help because you might not want to deal with big numbers until the end. If you have the limit of two things multiplied together, this is supposed to be a multiplication sign right here. You can do the limit of the product of the limits. In this one right here, this is important. If you have the limit of two things that are being divided, you can break it apart and do the limits separately as long as what? That can't equal 0. Things break if that equals 0. But these are mostly logical. You can factor out constants. You can break things apart along basic math operations. And I asked you to calculate this limit. You always check to see if you can do what first.
Factor out the.
No, you never factor first. What do you do first? Can you plug it in first? Can you plug it in? No. Then what do you try to do? Which is part of what are you trying to do by factoring? Simplifying. So next is try to simplify. Factoring is, and it does nicely. What is the factored form of the numerator? Someone raise their hand and tell me. Perry.
X minus 3 times x minus 2.
Correct. And what cancels, therefore?
X minus 3.
Leaving you with just?
X plus 2. X minus 2.
X minus 2. You plug in 3, and what do you get? 1. So what is the answer to this? 1. Done. Don't make them harder than they are. Don't skip steps. Can you plug it in? No. Then try to simplify. What's the...
I'm sorry, what do you mean? You mean plug the 3 in?
Can you plug 3 into that original equation?
And get?
Nothing, because you can't plug that into the original equation.
Look at the denominator.
Look at the denominator.
Oh!
Bingo! There it is. There it is. F. Say it's F. So here's f of x. And here is, this is x equals a right here. What is, and let's just call this y equals L, okay? What's the limit as x goes to a of f of x? What is it? It is L. What's the limit as x goes to a of h of x? It's also L. They're the same, right? So we have this third function. The third function is called g of x. It's always in between, so it can be equal to, but it's always in between, right? Correct? There it is, always in between. For this neighborhood around it, like that. By the squeeze theorem, what do you now know? Let's say, what do you know the limit of x going to a of, what is of that of g of x has to be? What does it have? It has to be L. Is there any way for that function to avoid being L there? For the limit to be? No, there is no way. There's no way for the limit to be avoided right there. Why is this helpful? Sometimes there are functions that you are not going to be able to evaluate very nicely for the limit, but you'll be able to come up with an upper bound and a lower bound that you can find the limit for. Do you understand what I'm saying? Kind of get it? Kind of maybe, sort of? Okay, so for example, let's look at this function, sine x over, yeah. Is it sine x over x squared? What do I want to do? The sine of, let me get this straight, hold on. Then if I multiply, can I multiply all those things by the same thing, and is the statement still true? Let's say I multiply, is x squared always positive?
Yes.
Yeah. So I'm going to multiply by x squared. I get negative x squared less than or equal to x squared sine x is less than or equal to. Do you agree that that has to be true? All I did was multiply by x squared. That's all I did. That's still true. What's the limit as x goes to 0 of negative x squared? It's 0. What's the limit as x goes to 0 of x squared? 0. What's the first rule of limits? What do you try to do? Can you plug in 0 into each of those things? Yes. Here's your f of x, here's your h of x, and here's your g of x. So, by squeeze theorem, what do you know? You know the limit of the middle, which is x squared sine x, is 0. The key to this was the original setup, right? You build the functions. What types of functions do you suspect we're going to use the squeeze theorem with mostly? Trig functions. Who said that? Why? Because trig functions nicely oscillate between a concrete upper bound and a concrete lower bound. Can the squeeze theorem come into play in other places? Yes. But when we use the squeeze theorem, it's mostly going to be used with trig functions, and it's mostly going to be used when I tell you to, or when you see things that really look like things you've practiced before. But here's your first example. This is the most classic example of where you can use the squeeze theorem.